All right, folks, welcome. Thank you for making the long hike out to this conference room. We were just joking that people who came here really want to be here and want to be in this session. So hopefully we'll do a good job of giving you some interesting information about blob storage and the design patterns and practices on top of it. We also have as a thank you for coming in a way, we have a social event right after that starts at 3:30, unfortunately on the other side of the building, but it has free beer. So hopefully that's a better motivation to kind of come back. It's right by the expo area. So please come see me afterwards. I'll give you a ticket so they'll let you in, and I'll walk back with all of you as well. So this talk is really about design patterns and best practices. Just as a kind of a quick level set, how many of you already know about or use blob storage? All right, all of you, almost all of you. Excellent. So this isn't really an intro talk. It's really more diving a little bit deeper into different patterns and different industries that use those patterns. Should be flipping, one would hope. Let's see. Okay, so I'll do my standard sort of very brief overview of Azure Storage Services and Blob Storage, but we'll dive pretty quickly into the design patterns. And what I want to focus on, or how the way we tried to build this session, was the application of those design patterns to specific data scenarios and specific industries. In some cases, we can't name the customers, but all of the patterns we're showing you here are used by current Azure customers. This is this talk in that learning sequence of blob storage talks. There's 3 more talks, one on ADLS Gen 2 tomorrow that really gets into that Hadoop file system support that we've added and that's in preview right now, and brings together Azure Data Lake Storage and Blob Storage. That is tomorrow afternoon. On Friday, we have a talk that really dives deep into the AAD, Azure Active Directory support in Blob Storage, the OAuth support, the RBAC support, and some other security and durability features. We touched on it very lightly in our session on Monday. I won't touch on it at all this session. But if you're looking at this, and I know it's been a long-standing ask for blob storage, both IT pros and developers, of how do I get Azure Active Directory to secure my blob storage? That's the session with all the details. And then one of the patterns we've added support for in the last year is serverless compute, specifically with storage events and event grid. So the ability to have blob storage data land on your blob storage account and have that kick off a workflow through a pub sub router, which is what event grid is, and go into functions or logic apps. That tends to be a pretty commonly used pattern nowadays, and it's really sort of enabled by having that storage events piece in event grid. So that's something that's interesting to you this session on Friday. I know a little bit late in the week, but it actually, we just build an app on the stage and kind of walk through what that architecture looks like. For those of you who are new to blob storage, there's a little bit of a learning track here. This is from the past few years of build conferences. That'll really kind of get you situated. We try not to repeat that content because we do want people to kind of go look at the new stuff rather than kind of just doing the same 101 talk over and over again. So storage, 3 services. We power block storage for Azure VMs. So anytime you're booting an Azure VM for the OS disk or the data disk, those disks are powered by Azure Storage. This intentionally left off all the embargoed stuff, but we now have standard HDD and standard SSD. Both of the standard SSD just went GA. We have premium, which is SSD backed, and we have the Ultra SSD, which is NVMe SSD backed. There was a session yesterday that kind of went into the details on that. We have file storage, both with Azure Files, which is our SMB as a service offering, and the service Azure NetApp Files that we've built in partnership with NetApp. Both of those have sessions in this conference as well. If you search for those terms, there have been significant improvements in Azure Files and FileSync, and NetApp Files is a brand new service that just went into preview. But the focus of this talk is blob storage and object storage. If you came to our session on Monday, we talked a lot about the different new features with a very specific emphasis on scalability and performance, particularly being able to drive up per blob throughput and per blob TPS for anywhere from 40 to 200x in the work that we've done over the last year or so. So that high performance, we'll touch on that a little bit today, but there's some exciting new features. AD we already talked about. We have a couple of other services that bridge these things. Data transport, there's a lot of news at Ignite about Azure Data Box, Azure Data Box Heavy, Azure Data Box Edge, and Gateway. So offline ingest as well as online connected projections of cloud storage, including blobs, into your data center. On the hybrid side, we have Azure File Sync. We have Azure, which we'll actually spend a good amount of time talking about today. So these are some other options if you're thinking about Azure Storage. Blob Storage is our unstructured data platform. It is what we call the durability layer for Microsoft, because all of our unstructured services, all of our unstructured data needs from our services, they run directly or indirectly into Blob Storage. And that's not just the Azure services, which of course use it, but it's also all of the Microsoft services. So if you're using anything on your Xbox, just to boot up your Xbox, it's going to make lots of calls to blob storage, table storage, and queue storage. If you go to Microsoft.com or MSN.com, anything you look at on those sites is coming off of blob storage. If you're using OneDrive or SharePoint, we have a speaker here from the OneDrive and SharePoint team, and he'll talk about how they have built on top of blob storage. So it is a very high-scale service that we rely on intimately. If blob storage were to go down, everything that Microsoft hosts on the internet probably goes down with it, right? So that's something that is a key piece, and it's exactly the same APIs, the same clusters underlying it. So there is no difference between what an internal partner team sees and what you see as a developer, as an IT pro. Same REST API, same storage accounts, same account limits and account scale and all of that. So the other piece about blob storage that's interesting is the integration with all of the services. And that's what this nice little pretty wheel is saying that there is integration points. Now, there are the obvious integration points like Azure Data Factory and things like that. You're using blob storage as a waste station for ETL of your data. Data lands there first, gets computed over, aggregated, and then pushed into a data warehouse. But there's also things like the cognitive services, right? You land data, you start a serverless compute workflow, and then you send something to the computer vision API, or you send it to the speech transcription API. Unstructured data kind of underlies a lot of things. Media, if you're doing anything with media, you're hosting video, you're transcoding it, you're delivering it to mobile devices, that runs through the Azure Media Services set of services. Use blob storage for storage of assets. So what I want to talk about a little bit is the data scenarios that we sort of frame around this. All of you use blob storage. This is pretty straightforward to you. If you think about the taxonomy, there's data for information workers, people who are, like us, who are all working with, Office and other documents. That is served by our partner team in OneDrive and SharePoint and Office 365 or Microsoft 365 more broadly, but the underlying base layer is Azure Storage. That same platform then is provided to you as developers and IT pros for all of your applications, your business applications, ranging from very high transaction, high throughput workloads that are served over the internet, all the way to deep archives and backups that you need for long-term retention. More and more people are collecting all the data they can, building it into a data lake, and then going and running the Hadoop ecosystem of apps and services against that and building BI and insights and things like that. That is something that blob storage supports natively. And the last one, of course, is hyperscale scenarios, which is canonically what object storage services were built for. Whenever you have tens to hundreds of millions of users with consumer-facing mobile or web apps, or IoT with possibly billions of devices all squirting small amounts of data back or getting a control plane, that is a service that's very well supported by the underlying data services. So what I'm going to do is also have this as a framework. We showed this yesterday, if any of you were in that talk, is just sort of highlight the different challenges or requirements that you have across all of these scenarios, whether it's be protection, security, scalability, cost effectiveness, access patterns, or hybrid integration. I've tried to layer the patterns against this. I'm not going to go into discussion about that because that was the session we did yesterday, but I'll use this as a sort of a narrative thread to tie back to our patterns. But what patterns are we actually going to talk about? The first one is that building hyperscale services. We're very lucky to have a bunch of those hyperscale services inside Microsoft, pushing us as a platform to be much better. So today we have Stephen Bailey, who's a distinguished engineer in the OneDrive and SharePoint team, who's going to talk about how that pattern applies to their team and the lessons they've learned. High-performance computing is another pattern. Now, this is historically, very much something that runs on premises, but is starting to move to the cloud. Especially when you look at it in industry, and we've picked autonomous driving because we've done a lot of work with automotive manufacturers and suppliers around this. This is a, pretty interesting area with a lot of computational challenges. So my colleague Klaus is going to come up and kind of talk to you a little bit about that space, a little bit about how we've had to learn over the last year or two how to satisfy the performance and scale needs of scenarios like this. Archiving. We've always, of course, as a blob storage service, supported large amounts of data. What's interesting to us, and this is learning for us over the last few years, is all the compliance and regulatory needs that go with archiving data, especially in regulated industries like financial services and healthcare. So we'll talk a little bit about that and the features we've built there. Another one is, burst computation. Again, with high-performance computing, people may not be moving all of that to the cloud, but they really want to move the peaks, if you will. They want to provision for a certain amount of computation on-prem and move the peaks in. So we'll talk about that as well. And that's specific, especially in the media and genomics industry, is something we see a lot of traction in. So with that, let's kind of dive right in. I'm going to invite Stephen to come up and talk about building hyperscale services. Thank you, Stephen.
Hey, everybody. So I'm Steve Bailey. I run engineering team for OneDrive and SharePoint. OneDrive and SharePoint are gigantic customers of Azure internally, as Vamshi was talking about. It's great for you guys because we push Azure pretty hard. We give them lots of feedback on reliability, performance, cost reduction, new features that we need to just make OneDrive and SharePoint awesome. And so I'm going to talk today kind of just a little bit more generally broad about sort of like OneDrive and SharePoint and what we've sort of just learned over the years about sort of scaling and growing the service. I'm sure all you guys are building services on Azure and maybe specific to storage, but generally building services. And so we'll talk about 12 or so lessons that we've learned, sort of things not to do, through our own mistakes over the years. And so hopefully you guys can learn from that. Wrong way. There we go. Yeah, so the first lesson that we've sort of learned over time is around capacity. Capacity can be anything from sort of networking, compute, blob storage, memory. And so, managing resources on a large-scale services is essentially one of the first things that you got to figure out. If you're sort of brand new building a service, you probably run into the first problem of you've ran out of capacity and things go down. That's sort of not a mistake that you can keep making. And so, you can be underbuilt. And so that's when you run out of capacity, things fail. You can have hot spots in your system where you have something that's you have a large system and you have a piece of it that's hot and the rest of it's not hot, and so that you have undistributed load, and so that's not a thing that you want to end up in. And so you can be overbuilt, which is essentially a waste of money. And if you're a really large scale service like us, being overbuilt could mean millions of dollars of sort of unused resources just sitting there idle. And so managing that sort of fine line of having enough capacity to keep growing, but not wasting too much money is a critical thing. You can have sort of asymmetric capacity problems, where if you're building a service and you have like a couple services behind the scenes, where one service is big and the other service is small, one service can sort of overwhelm the other service. So that's not one that you want to have. Failover, if you're building on Azure Storage or you're using geo-replicated storage, you have to think about like, well, if something goes down, I need to fail over all of our workloads somewhere else. Do I have capacity where I'm going to fail it too? If you don't, then it's going to be hard to fail over. So everything that we do in OneDrive SharePoint is really about trying to even out our overall distribution of our load and traffic across all of these different resources. We found that the more sort of decoupled that we can make these things, the better. If we have some sort of workload that really requires a massive amount of compute, we can do that. It doesn't mean we also have to build out storage with that. We can sort of build out just compute. And Azure, is basically the thing that gives us all these different building blocks. Sort of lesson 2, be resilient to hardware failure. OneDrive SharePoint started, have been around for a very long time before Azure existed. And so, and I've been with OneDrive for 12 years and SharePoint. And so we've lived the world of building that infrastructure ourselves. And so when Azure started to grow up inside of the company, we became big customers of that. And we started to move most of our infrastructure over to Azure. And so we've lived the world of building our own infrastructure and now lived the world of sort of having Azure do it, which is wonderful. But you don't want to build this infrastructure yourself. It's very difficult, very complicated. Everything from knowing if a disk drive failed in a server, and having that automated repair happen within a data center. Having, just everything from, there's been I list a few different sort of outages that have happened, in our world, just raccoons chewing a cable, take a data center down, lightning strikes, fairly recent event that happened. Just building all of the infrastructure that it takes to run, compute, networking, storage, that it's difficult, and then making your service resilient to those failures is important. And so Azure provides most of this infrastructure for us, dealing with hard drive failures and things like that. But even in your service, if you're building on top of Azure, you still have to have some knowledge about being resilient to certain failures. If a cluster goes down or a data center goes down, what do you do in your application to handle that? And then if you have clients talking to you, are they resilient to you failing over? These are all problems that you have to solve. And so this is where we spend a ton of time in learning and kind of learning the hard way too. Lesson 3. This one is, a little bit different. This is really about, sort of like this feedback loop. Everybody's probably heard the word agile, all those, types of things. Microsoft, 15 years ago was we shipped software onto a CD, and had a 3-year update cycle. Today we ship every day, maybe multiple times a day. And so what we've learned is that that feedback loop of like shipping code to customers and getting data back, the tighter that we can make that loop, the better it is. It's dangerous, so you got to be careful. I have next slide about that. But that data loop of just getting feedback back to engineers so that they can keep iterating. We're just in a very iterative, world now in terms of software development. And so the systems that we sit on, for being able to enable this sort of real-time feedback system is a bunch of Azure systems that we use. Azure monitoring. Different systems that we can use to get there. The Azure DevOps system is what we use for OneDrive and SharePoint for building, managing the release of our software. All these systems have to allow us to go as fast as we need to go in case we have some incident that we need to respond to, or as slow as we need to go to, depending on the type of release that we're doing. Lesson 4. So in the world of running big services, if you're going to fail, you should expect that you're going to do something that's going to fail. You're always, you should plan for mistakes. And so the best mistakes are ones that happen small and fast. The worst thing is you have a bug that ships to the whole site and it impacts your entire customer base. That's the worst possible thing that we can have happen. And so our real focus is around like isolating mistakes. And there's lots of different techniques that we do, testing your software Having automated testing is obviously the first line of defense. You can catch bugs before they get to customers. But the tests aren't always going to catch everything. So then the next step is slow. Ship it slow and then fast. Make the software prove that it works before you give it to all your customers. And prove that it works is sort of this new world of like having real-time monitoring on your software. And there's some services in Azure that help you do that. And that really gives you this sort of feedback loop that, reliability and quality of service that you get back from the service to know if the thing that you just shipped is working or not. And if it is working, then you can start to ship it faster and faster. But that data loop is the thing that you have to rely on. Our software is just too complex for people to have to look, for problems. And really like the worst possible thing is when customers call us and tell us that we just made a mistake. And we didn't detect it ourselves. And so, we sort of have this saying that customers aren't our monitoring system. We're obviously not always perfect, but that's our goal is to find the issues before customers call us. So there's another type of event that we've had where, we do all this internal monitoring on our service, and we think we're great and everything's up and healthy, but customers can't reach us from a certain, customers can't reach us from a certain place. And so, there's lots of, the customers at the end of the sort of networking, end of the sort of stack. And so there's lots of things between them and maybe the services that you're running. And so all sorts of things can go down. IPs can, the ISP can do something that affects your service, or, DNS, there's been DNS outages or DDoS attacks in the last few years that have impacted lots of people. There's lots of proxies running inside different corporate IT environments. IP reputation services can come in and like blacklist your IP address, and you have no idea why. And so really like the key here is like monitoring your service from the customer's point of view. Whether that's like putting some, maybe you have an agent running an Azure VM in the region that your service is running in, just to sort of like, try to go through the same networking stack that your customers are coming through. And then firing alerts if you see something from the outside that's not working. This next lesson, this one's kind of a little bit more complicated. But when you're building large-scale systems, the worst thing that can happen is sort of what we kind of call gray failures. These are kind of things where you start seeing some sort of like slow progression of a latency, like regression happening on the site. And so it's usually like something happened where you shipped some Sprock to a SQL server and it slowed down some query. And then all of a sudden, like everything that's calling that server starts to slow down. And then everything that's calling that server starts to slow down. And if you don't protect these services, they eventually like connections start to pile up on these services. And then they run out of memory. And then it cascades to other services. And then eventually your whole site's down. These are kind of the worst types of outages that we have because they're hard to detect. It's better for a call to some other service to fail fast if it's going to fail, rather than like that call take a while and then fail. And so, but that's hard to detect. How long should you let it happen? Like how long should you let a call take before you decide to time it out or kill it? Sometimes people don't even know what their timeout limits are on their services. Maybe it's 10 minutes, maybe it's 2 minutes. But the worst thing is you call a service and it normally takes maybe milliseconds, and now it's taking 5 seconds. Is that too long? We don't know. But the best thing you can do is kill it quickly, because if they start taking longer at scale, then everything's going to sort of like congest up like a big traffic jam. And so the protections that modern services usually put in is different connection limits, different resource limits on the servers, so that they can start failing things much more quickly before servers get to a point where they can't even respond. Which is sort of the worst case. So this one is kind of interesting. Caches are wonderful. Like Azure Redis is wonderful. We use it really heavily inside OneDrive and SharePoint. But they can be really dangerous. A lot of times we use cache to sort of speed up. If we're calling another service, we'll cache the responses from that other service so that the next call is fast. And we might also be doing it to sort of reduce the load on that other service. But what happens when Redis goes down and your cache is now gone? What happens is you now start calling that dependent service way faster, way more than you were before the cache went down, and that service might not have been used to that type of load. And so that dependent service might get overwhelmed and stop responding and slow down, and then you might have a situation where you can't bring things back up. And so we've had outages like this before in OneDrive SharePoint. And so what we've learned is that when a cache goes down, we have to detect that. We have to essentially throttle the recovery automatically. It can't be a human that does this. The code has to recognize when this has happened and then essentially bring the cache back up sort of progressively. We might be failing calls outward when we're doing this to protect the service, but we have to bring it up in sort of a reliable way, even though we're still failing some calls outward. It's sort of, we're taking like a reliability hit in order to get the service back into a healthy state, which is, in the world of trade-offs, that's a fine trade-off to make. So yeah, lesson 8. This is always an interesting debate at Microsoft. It's like, well, just reboot the servers. Like, everything will be fine. Like, just reboot them every 24 hours. Like, we should just do that. It's a lot easier than trying to find memory leaks. I have a different point of view, which is don't reboot the servers. If you have to reboot the servers, it's a sign of something bad. And you should have your engineering team figure out what's going on. Like, you probably have a memory leak. You have some resource leak. Those are bad things. It's like a dirty sink. If you keep putting more dishes in that dirty sink, it's just going to get dirtier. And so, keep it clean. Don't use reboots to deal with memory leaks. That's sort of like the key point, because over years and time, you won't notice new memory leaks. That's really the issue. Is like once you introduce that first memory leak and you start using reboots to sort of recover from them, it's easier to just let that second memory leak in, or that third memory leak, or that fourth resource leak, and then all of a sudden you just have, now you're having to reboot every hour. And it's hard to reboot services in a large scale and not take some sort of availability hit. And so that's just, you guys might have a different point of view, but that's my point of view. Lesson 9, humans don't scale. They like to sleep and spend time with their families. And so we've learned that it's not just good for customers to run a healthy service. It's good for the people who work on it, so that they're not waking up and having to come into work on the weekends and work late. You're not going to attract a lot of talent to your team if you have a really unmanageable system. Humans are great, wonderful, but they forget things, and they make mistakes. And so so we've learned over time that automating as much as we can is the most critical thing we can do. And I think the biggest thing I've learned is do it as soon as you can. Even if you feel like you have a small service, that thing might get big eventually. And so start that sort of process of automating those tasks that you're sort of doing sort of manually now. Automate them so that when it gets bigger and bigger, it's easier to manage. This was kind of simple. These types of outages are sort of, hopefully in the big services, things that happened 5-6 years ago. But I've had this outage in OneDrive before, and people come and it's like, why'd you let our cert expire? And there's never a good answer to that. It's yes, it's basically oops. And now our service is so complex. We have thousands of Azure accounts, and access tokens to those accounts that have to get rotated on a continual basis, certs everywhere. And so this is kind of another one of those things, really sort of the humans don't scale thing. Humans will forget to renew a cert if that's your system for that. And so you can build a system. We use Azure Key Vault for managing all of our secrets. We have some service on top of that helps a little bit with sort of rotation and expiration notification, but automate all that type of stuff. Don't let a human have to remember to renew a cert. This one's pretty easy. I think everybody kind of gets this one. But complexity is like the enemy of reliability and performance and all that stuff. You guys can read the slide, but it's really, the thing we've learned is that the more homogeneous our service is, the more similar it is everywhere it is, the easier it is to run it. the biggest one we always had is like, well, we deployed the service to like one cluster and it worked, and then we deployed it to the next cluster and it stopped working. And it wasn't because of bad software, it was because of different config environment or a different environment that was just different and caused things to break. And so, just trying to make everything the same is critical. We always kind of call it snowflakes. We don't want any snowflakes in our service. Lesson 12, this is like the kind of the final thing is about the culture of the team. It's sometimes difficult to get engineers to really value the fact that they're running a service that, it's like the power company. It's, your utility service. OneDrive and SharePort, we kind of think of as like a utility. It's like the dial tone for your file system now. We're sort of replacing your local disk drive for your files. And if that thing's not up all the time and reliable and performant, and withstanding data center failures and things like that, then we're not doing our job. And so we focus really heavily internally on building that culture. Same with Azure, of just really focusing on those deep internals and fundamentals within the team. Yes, we have to keep growing the product, and we have worthy competitors in the OneDrive SharePoint space that we have to keep up with and beat and all those things. But like that culture of like fundamentals is really the big thing, and that is like total culture. And then like the final thing I'll leave it with is just OneDrive SharePoint. We love Azure. We don't want to be building that stuff. We want to be winning in the sort of enterprise content management, file sync and share space. And if we're building all this unique infrastructure, the Azure's building, it's sort of a waste of our time. We want to be building differentiated value for our customers and focusing on, scenarios and things that make our customers' lives better. And so, we use a ton of Azure stuff. We're a huge customer, and so anyways, that's it. I'll take questions at the end. I'll be around at the end. Thank you.
Thank you, Stephen. It is great, and we have learned a lot with the OneDrive team and leading to a lot of platform enhancements over the years. We're going to talk a little bit about high-performance computing on Azure. And sometimes high-performance computing applications are off-the-shelf applications that people are running on premises today and bringing them into Azure where they're not used to run in a cloud environment. We're working, and you will see some of these fruits from that, working to make enhancements in the platform to make these off-the-shelf standard packages run well in a cloud environment. So we're anchoring this part of the talk in one of the HPC environments called autonomous driving. And what you're looking at here is the dev test workflow that we work with the industry on defining and what it looks like. I am not going to try to explain all of it to you, and this is not the purpose of the talk to make you an expert in autonomous driving dev test workflow. But I'm using it because I want to drill in on a couple of these and show what we have done. So if you look at the leftmost part of it, you see the test vehicle. So in autonomous driving is a lot about test vehicles driving around the road across the world collecting data, right? All sorts of data that they're then ingesting and storing in a storage system, in our case, in Azure Data Storage. Then there is a process to curate this data, finding the pieces you need, sort out the pieces you don't need, and then they go into various pieces like, for example, sensor algorithm testing, where you can have a developer say, I have several algorithms that I could apply to this. How do I test this using all the data? So I'm running what we call re-simulation, basically testing the new algorithms on top of the already collected data and see how it behaves, score the algorithms, compare, etc. And then there's the training aspects of it, where you're training all the software to identify people, road signs, etc., etc. So let's first talk about the ingest and store. How do we get started? So this sensor data that is in every vehicle include things like LiDAR, radar, video, telemetry, etc., etc. It actually can amount to up to about 20 to 70 terabytes per vehicle per day. Right? So if you have a relatively small, even with a small test of test vehicles, say 10 to 100, we can talk about a data ingest of 1 petabyte of storage per day. Right? That's a little more than my Word document and PowerPoint we created for this talk. So the options you have to deal with something like this is you have these massive data ingests with the DataBox family. Now, I'm not going to spend a whole lot of time talking about DataBox. That's not the purpose of the talk, but I just want to make sure you're aware of it, that there are several offline data transfer options with DataBox. In this case, we will most likely lean towards DataBox Heavy because that stores exactly 1 petabyte of capacity. There's also the more connected devices, the DataBox Gateway and the DataBox Edge. Especially the DataBox Edge has the ability to actually run some of these processes out on the edge to curate the data, so you don't send more data to the cloud than you actually need. You sort it out there instead of doing it in the cloud. So you reduce the amount of data that you actually need to send to the cloud. Now there's also ExpressRoute, and hopefully you have all seen the announcement around ExpressRoute this week supporting 100 gigabit per second network links, right? And so let's take a look at what that looks like. So I have this little short demo, and hopefully the clicker works. To get the demo set up, what we're showing is essentially we have a set of servers. We have 4 Hyper-V hosts, so we don't actually have test vehicles. We're simulating the simulation, if you will. We have 4 Hyper-V hosts in Seattle. Each Hyper-V host runs a VM, 3 VMs, so there's a total of 12 VMs. And each VM has a 10 gigabit network link. It is all pushing data through the ExpressRoute 100 gigabit link into a single storage account into Azure. So the demonstration here is a little rough, but what we're doing now is we're basically sending a command to each of the 12 VMs to go push its data into this storage account. So they're each sending their own data set. And what you can see on the right side, if you bring out your binoculars, is you can see Task Manager for each one of these 12 machines. And what you should see if you look at the Ethernet portion, that each one of them is pushing 7 to 9 gigabits per second, which is just very close to the 10 gigabit that network interface that they have. And if you quickly add that up in your head, you will see that this pushes more than 90 gigabits per second into Azure for these 12 VMs. So that is showing the 100 gigabit network link from ExpressRoute and the fact that we can push 100 gigabit a second into a single storage account. If you calculate it in bytes, it becomes 12.5 gigabytes a second. That's to a single storage account. Actually, in a talk yesterday, I showed it to a single blob as well. But I'm not going to repeat that here because you were there, right? And you all saw it. And it is recorded in case you want to go back and see it. Now, so the resimulation part is the next part we want to talk about. So resimulation is, as I mentioned, is the ability to bring back an algorithm back into an environment that was already recorded and testing out algorithms, comparing them to each other, figuring out which responds best to various conditions. In that case, we're talking about a very large data set. So this resimulation runs across tens of petabytes of data. It is highly parallelizable, if that's a word. If it isn't, I just invented it. So you can run it across many, many compute cores that each operate on a slice of the data set. And it's the general expectation that this completes in about 2 weeks. So if you do the math, that actually comes down to massive throughput requirements, 25 to 400 gigabytes per second of throughput required. So if you're up at the upper edge on this, you could see, okay, in that case, I probably need to shard my data across multiple storage accounts. And that's how you would deal with that currently until we up the limits again and again and again. Eventually, we'll be able to do it in one account. And if you need to know how to do this, come see us, and we'll work with you on designing something like that. Not only do you need to read through the entire data set, you also need to write out results. And the results are close to 70 to 80% the data that you actually read. So you have an equal amount of almost equal amount of write performance that you need in the system. So in many cases, what happens is you read data from one storage account, you write it out to a second storage account. So you create that loop, and then the developer goes back and analyzes the result from the output and can see what happened. So I have a little video that I want to thank Electrobit for helping us show. It's their video, and they graciously let us show it here, that actually visualizes what this resimulation looks like. So what they're seeing is effectively a car driving through an area, scoring what it sees objects. The green is where the car can go. The red is where the car shouldn't go. Right? And then right there here, they're running two algorithms side by side, yielding various results. So you can see the one on the left saw more red than the one on the right. Right? So I'm not an expert in these things, absolutely not, but it's sort of an interesting illustration of what it is that is happening in this scenario. The other part I mentioned was the whole perception training. Perception training is basically what does the car see, or the sensors of the car see, right? How do I detect traffic signs? How do I detect various traffic signs so I can react to them? How do I detect pedestrians, et cetera, et cetera? And we need to make sure that these vehicles detect all these things. That is an exercise that executes on a lot smaller data set. The data set is read frequently over and over and over again, which means this is a kind of data access that benefits strongly from having a cache in play, right? So you can have a cache that's very close to the compute layer because you're reading, you see, if you run 100,000 iterations over the same data set, guess what? You just read the data 100,000 times. So you might bring that closer to increase or actually reduce the runtime of the entire job. So to illustrate that, I'm going to show you a different demo. In this demo, we're looking at a storage account here. We're going to open it up and see what do we have in this storage account. We got a container in here named container. Brilliant name, right? Who would have thought of that? And then we're refreshing that and see in that we have a blob. This blob is 1.5 terabyte in size. Okay? Let's read that blob, all of it actually. So I'm going to start this program that uses 4 VMs that are actually reading this blob in parallel, or actually reading 25% of this blob in parallel. So here are the 4 VMs. This is network, or so perfmon showing the throughput to each VM4. So let's help it up a little bit and accelerate time. And you can see how we get, actually the yellow one is running a little faster than the other ones. This is awesome. It's probably going to finish first. So now the VMs are finishing up, and you will see that the network throughput drops, and we will report the output in the lower left corner. And you can see that 1 out of 4 jobs are completed. We should see the other ones complete real soon. 2, 3, 4, excellent. So let's zoom in on that. So what we just showed was 4 VMs. Each one is a D64 that has a 30 gigabit interface on it. And we just read all of this data in 106 seconds, coming to 120 gigabits a second, which is exactly on the dot 30 gigabits times 4. So we read the data at the network interface speed of the VM. So what you actually saw in action is a new capability we call high throughput block blob. It consists of both write enhancements and read enhancements. The write enhancements are around ingesting larger blobs with high throughput, which is what you saw in the first video, right? We wrote this at 100 gigabits a second into a storage account. What you may not have noticed is that the write throughput is instantaneous. If you've tried to push a lot of data into a storage account previously, you would have seen that we sort of ramp up. You need to warm up to get to the high throughput because of partition splits, and then it cools down. With high throughut blob blob, you get the performance right away. The other part that is pretty cool about it is the whole concept and issue with container naming and blob naming, and what if I have what we call sequential names or log files that just have like a date at the end that makes the difference. That is a non-issue. And this will be available at the end of 2018. The read enhancements for this that we just demonstrated are already out there, so you can egress larger blobs with high throughput and accelerate frequently read blobs by a caching construct that we have built into the storage system. There is a session on Friday, serverless compute architectures with Azure Blob Storage, where they'll build an application using high throughput block blob. So want to see what that looks like? So here's the architecture in Azure Storage is we have at the bottom of the stack, we have a stream layer that stores all the data in Azure. It takes care of the replication of data, deals with the failures in hardware, bit rot, et cetera, when bits flip on a hard drive. Above that, we have the actual namespace, where we have the partition servers that provides the table, queues, and blobs that you see, as well as the front end, which takes the HTTP requests, handling the decryption and compression of the data, et cetera. So before we had high throughput blob, this is what would happen if you wrote a movie file of this, in this case, 50 gigabytes into Azure. You break it into blocks, hence the name block blobs. Right? And these blocks are then written through various front ends because you can have multiple machines writing this. Now, because of the strong consistency, et cetera, we have this, the single blob is served by a single partition. So it goes to a partition server. And then it gets spread out across the stream servers after the fact. But what you see here is the architecture we had before high throughput blob is essentially an hourglass effect, where all of the things are funneled through a single partition server, which is what limited the throughput. So with high throughput blob, we still do the same thing with the blocks themselves, but instead of going to a single partition server, we can now go to, in this case, 2, but potentially all of them. And that also means that we spray across more streams on the back end in the stream servers, and therefore we can get to a point where we utilize the entire storage cluster for write throughput, which is why you saw the ginormous ingest numbers we saw. And there is a bunch of tools and services that are taking advantage of high throughput blob, it's including AZ Copy V10, which is in preview. ADLS Gen 2 uses high throughput blob. Databox supports high throughput blob, so when you push data into Azure through Databox, and Azure Data Factory, et cetera. So, all right, thank you.
So another pattern that I want to talk to you about, as I mentioned, was archiving for compliance and what the asks there are. Essentially, the first thing about archiving is you need very inexpensive storage. The archive tier that we introduced at the end of last year and is in GA in quite a few regions is the least expensive cloud object storage available. It's 50% cheaper than our competition. And we will continue to drive that lower over time. We're making some pretty fundamental immediate engineering investments as well as some very long-term investments in research to kind of drive that closer. So that's something that you should think about when you're thinking about archiving is, look, is this data that I can wait a day to get back? If it is, put it into archive, right? An order of a few hours is what we say. But think about that as your rough equivalent of tape, right? If you probably have a DR system, you probably have it on tape today. If you can use this, this will be way faster than tape and dealing with tape generation, migrations, all of that. This is sort of what the archive tier is for. I highlighted also, interestingly, the premium storage. The terabyte cost is huge. Object storage on SSDs, you can, because the dominant cost at a high transaction workload, it's all about transactions. If you look at your bill and you're doing more than 50 transactions a second, I guarantee you you're paying more money in transaction costs than you're paying in gigabyte costs. So that's why that exists. It's 65% lower transaction costs than the other tiers. So either end, it's interesting to look at. But the other thing that we do for the archiving piece is make the API consistent. As you're all developers or using packages that use Blob REST API under the covers, the last thing we need to do is give you different API surface areas, different endpoints, and make you move all the data between services. That is the worst kind of thing to be doing as an app developer on top of our platform. So we don't make you do that. You have hot, cool, and archive tier. They're all one API. You just call a REST API to move the data down tiers. It's just a metadata operation for you. We start billing you immediately at the lower tier, and we'll move the data asynchronously on the back end when we can. So we manage IOs and all of that, and we decide when we go from our hotter disk clusters to our cooler disk clusters. When you're coming back up the other way, it's also near instantaneous because you say, go from cool to hot, we'll immediately push that onto an SSD or something on the cooler disk clusters, and we'll over time bring it back. So we take care of all of that stuff underneath the covers. We have that on an API level, so you can call it on a per object level, or we have it as a policy lifecycle management. You can just say, all my objects older than 3 months, push them to cool. Everything older than a year, push them to archive. 5 years, delete it. That you can just kind of codify in a simple JSON object, push it, and we'll apply it against your account, a container in your account, or a subset of objects in your container. This doesn't work today for the automatic lifecycle management, the tiering. For premium, the new premium service that's in preview, to hot, cool, and archive, but that's something that's coming as well next year. So quick double click into data lifecycle management. You can do it on account level, container level, or you can have a prefix on your blob and we'll apply it. We run that once a day, and we go do essentially a blob inventory walk, and we'll go do that. And the reason we provide this to you is because we can do more efficient things on our backend and how we look at inventory. So even if you have tens of millions of objects, if you had to do it, you'd have to list all the blobs back. We'll do this more efficiently on our side. It's in preview now in 3 regions, and it's a relatively reasonable cost, again, because we're not trying to necessarily make money. We're trying to make sure here that there's a simple, easy convenience factor for you to store your data on our platform. We're also continuing to expand archive availability. We have 8 new archive regions announced at Ignite, and our commitment is to make sure archive storage is available globally in all the regions that we have Azure Storage in. So those are the new 8 regions in Europe and in Asia and Australia. So what about the compliance piece, right? That was archiving. What about compliance? One of the things we learned when we started going down this path is, again, these regulated industries have lots of interesting rules and things that they have to certify to other bodies. In financial services, it's the SEC, it's FINRA, there's equivalent bodies in the EU, and you have to show to these regulatory bodies that the data you write is tamper-proof for a certain amount of time, right? That's a very common pattern. I don't know how many people call their brokers anymore. That's a term that gets used, but I don't think anybody actually does it. But if you ever call customer service in a financial services thing, they're actually required to record. That's that warning they're telling you, we might be recording this call is actually required by the SEC. And then they require them to show that they haven't tampered with them for N years. So that sort of stuff requires tamper-proof storage or warm storage, write once, read many storage. That's what we've launched. Just went GA actually last week. The thing that we did here is we said, hey, what do we need to go solve this? On-prem, this is a massive problem. You have to go buy these expensive systems, put them in there. You have to deal with data migration. It's just a god-awful. How many of you have to deal with warm storage, just out of curiosity? A few of you. So some of the folks who have had to deal with it know that it's a major problem. Here on our side, it's very easy for us to do this and build it into our platform, make it an easy API call for you. It's available in all of our blob tiers. So one of the interesting things, again, is that you can move data between tiers without violating the tamper-proof thing, because it's about tamper-proof from external. You can move data between storage systems. So that's something we do. So you can have this functionality available on hot data and eventually age it all the way into archive and then delete it when your retention period requirements are done. So that's what that feature allows you to do. We also support the notion of legal hold, which is another very common concept in compliance, is there's a litigation or there's a case or something happening, all the documents or all the mailboxes for the people involved in that litigation, whatever the case may be, need to be held and need to be proven to not be tampered or deleted during that period of time. So we support both of those options, and you can go look at that. Another interesting thing in preview, certainly we expected FinServ and healthcare. There's other places that need this. Media and entertainment, they actually want this stuff because they want archiving. They want to know that their master copies are never touched and modified in any way. So it's not a compliance thing. It's just the industry operates that way, and they like this feature for that sort of thing. Public safety, body cams, for example. You need to prove, for legal reasons, that the body cam video was never modified after it was uploaded from an officer, right? So those are things that we didn't anticipate when we started down this path, but those are all use cases that we satisfy. So I wanted to kind of dive into a couple of customers. Unfortunately, some of these I can't name the customer, but they allowed us to use the story. These are all stories of customers that are running on our platform. These are the partners involved. What this is essentially a hedge fund that has to record all calls and has to store them. So there are two partners here, HubStore and Redbox. Redbox is actually the company that captures voice recordings and makes, saves that off to disk. HubStore is a partner of ours that takes data on disk and pushes it into blob storage and manages that chain of custody, lifecycle management, and uses immutable storage underneath the covers. So it does all of that. And it actually then uses our cognitive services to do things like audio transcription and search over those call records, because if you can do that, that makes it so much more useful than just here's a bunch of MP3 files or WAV files. So they're using the cognitive services to go do that. Another customer, this is a different partner, BRK337373, is using this stuff for a residential mortgage company. And they have e-discovery needs. So this was an interesting thing where they had a few hundred terabytes of data just in a place that wasn't compliant. They were getting various warnings from various bodies, and then just weren't able to meet the e-discovery and compliance requirements. So they were getting this thing, they didn't know where the data was, even if they wanted to satisfy the e-discovery needs. So instead, they've moved to blob storage through BRK3373. And BRK3373 is also cool in that it does this very similar things. It takes all of your emails, your videos and audio, and runs all of that through things like Azure Search, Azure Cognitive Services, transcription, the language transcription. So they can actually take emails written in Japanese, Korean, Hindi, whatever, and make it searchable in English, right? So because again, lots of companies have people around the world working with them, and they need that sort of thing to fully meet e-discovery needs. In healthcare as well, this has become an interesting thing. We have customers now that are using immutable storage for things like simple things like this company, this pharmaceutical company actually needs to maintain, and this is again stuff that comes from the FDA and other things, all the images of devices of their ex-employees, because if they ever get sued, they have to be able to prove here's what was happening. And they're getting over a petabyte of data just to pain to maintain this on-prem. Immutable blob storage made it possible for them for the first time to move it into the cloud and keep it in hot or cool storage, because they do need to kind of go look at this stuff, pull it back, run queries against it, that sort of thing. So that was a very cool customer scenario that we were able to solve with this feature. And this was all while it was in preview over the last few months. Another example is long-term medical imaging retention. And this is something that we're all more familiar with perhaps as consumers. You go in, you get an X-ray, you get an MRI. The hospital is required by law to maintain that. And they also have to prove, if you ever sue the hospital, they have to prove that they maintain it in a tamper-proof state. So this is a company called Delphinus Medical Tech, also HubStore again, and adding about 20 terabytes of data a month. And again, this idea here of being able to use blob storage makes their cost structure a lot cleaner rather than having to keep growing their storage arrays, and they can just pay for what they use. The other nice thing is that this becomes fully self-service. HubStore actually goes and fetches. So if a medical staff person has to go get the data, they don't actually know that there's cloud storage behind the scenes. It's a read-only pattern, so you're not modifying the data. So they actually make that fully transparent for them. So some pretty interesting scenarios have kind of fallen out of that core feature we've built around immutable blob storage. So if there's something that you look at and you're like, it would be interesting for me to make data immutable, then please go look at it. The one thing that we would caution, and I've run into this, my colleagues have run into this also, if you're testing this feature, don't set the timeout to things like 1 year. because we will respect that 1 year, and we will not allow you to delete the data in that container for 1 year. So just keep that in mind a few days or whatever. We actually sort of allow you to set it anywhere from 1 day to 400 years. I don't know if any of us and the storage system will be, I hope the storage system will be around in 400 years, but we do allow that in the config, so be careful when you try that feature. So now I'd like to switch to burst computation HPC application migration and ask Rebecca Thompson, who's the leader of the Azure product management team, to come up and talk about this scenario.
Okay, hopefully my mic, yes, it's on. And I think I have too many slides for the time allocated, so we're going to try to do a little bit of cleanup here. We're playing a video first, are we? Okay, so this video you're going to see, Azure is a specialist in high-performance computing applications, working with vendors who work with special effects studios. This is Mr. X, which is a Technicolor production, and these are all productions that most of them you will recognize that were done on Azure technology for rendering.
Don't be afraid.
At some point, we have to face up to who we are, who we're meant to be.
What am I? I move my mouth like him. I make no sound like him. What does that make me?
I'm gonna kill every last one of them.
Okay, so that was again Mr. X, a Technicolor division, and special effects using the Azure technology. Not sure how familiar you are with Azure, but Azure was a technology company started by a few Carnegie Mellon professors, started in Pittsburgh about 9 years ago, and was recently, just this year, in early 2018, acquired by Microsoft. Really, the Azure expertise, what we built our expertise on, was high-performance read-write caching for HPC workloads. And principally, we got our start first in the media entertainment, in the post-production, cloud rendering, render farm performance. I think what, we all love going to the movies and love watching things on Netflix and HBO and Showtime, but, and I think people are aware that special effects are pretty, intense to create, but they are probably way more intense than you think, and almost everything you see in a film, whether it's, explosions or fires or things like that. Those are computationally intense, but there's simple things like sand. So for example, when you see a war movie and it's set in the desert and they have sand blowing through there, no one's going to actually ruin a bunch of helicopters and vehicles and stuff like that by subjecting them to an actual sandstorm. So those sandstorms are all models. They're all models. It's all special effects. It requires a mass amount of computation for all the special effects. But and the challenge that the movie studios have is the challenge every industry has. Even though we look at the box office returns for like the Marvel pictures and we say it's $1 billion worldwide box office, oh, they're getting so rich. The budgets for in particular for motion pictures, are shrinking and shrinking and shrinking, and they have a per project budget. So even though the profits on them go up or the box office goes up, it's not like the technology people have endless dollars to spend. So they're always looking for more creative ways to get more processing out of their current IT infrastructure, and that includes now, and we'll talk about that. That includes now going to the cloud. But it's not all media and entertainment. That's the fun and glamorous part, I think, of the HPC workload. There's really serious workloads that where the Azure product works really well. One is in life sciences, for example, genomics and bioinformatics pipelines. It shares a lot of the same characteristics as a media rendering workload. A lot of small files, very computationally heavy, and so it's a good application not to be moved onto the cloud either in a hybrid fashion or all in. The next is financial services, capital markets, so hedge funds, things like banks, hedge funds that are running Monte Carlo simulations, back testing. These could be models that are not run on a regular basis, but they need like episodic compute. So those are good of your customers as well. Energy, so you'll find a lot of your customers, particularly in the upstream energy, oil and gas industry, things like seismic processing and reservoir simulation require a lot of computing. And then lastly, what Vamshi had talked about, and Klaus had talked about, advanced manufacturing, things like autonomous driving, but also EDA type of applications, which also have a lot of processing in them. So your traditional HPC environment, I mean, it's got a couple things, there's a couple things in common with, with all of these different environments, from media all the way to, manufacturing, is they've got a ton of infrastructure on-prem, there's a lot of compute, there's very few humans involved, right? So you may have tons of clients, but the actual human beings using them are pretty minimal. They don't spend a lot of time calling IT to complain about things, because it's generally a compute farm. They tend to be file-based workloads and have a ton of data. So for that reason, they've been laggards in moving to the cloud. They're hard to move to the cloud, especially an all-in cloud application. So these traditional HPC environments have really been the first to look at more of a hybrid type of deployment and getting the application running into the cloud. And the first thing that people think about when they're moving workloads to the cloud is, I want to smooth out the peaks in my performance. So for example, I have built my infrastructure for, let's say on an average, week or whatever, I have 20 to 40,000 cores, compute cores that are running my applications, and I can run at a steady state. But if I get a spike in demand, if someone needs a deadline pushed up, or I have two projects that overlap, then I'm out of compute capacity, and people are going to have to wait. And that's a great opportunity to take and move some of those workloads to the cloud in a scenario we call cloud bursting. But once people do that, that's sort of like the first step for the cloud for HPC applications. Then people start thinking about, well, gosh, now that I've got some data in the cloud and I'm doing some processing, can I take advantage of things like machine learning, artificial intelligence? Are there any analytics applications? So it really opens up a whole new world of possibilities once you start moving some of that data to the cloud. So what is Azure? Quickly, it's a high-performance, scalable read-write cache. It's a virtual. We have a physical appliance for on-prem. I'm not here to talk about that. I'm here to talk about the virtual one that sits up in the cloud. And essentially what it does is it scales, identifies kind of the hot data that's going to be processed in the cloud, and it can pull data from either on-prem storage, file-based storage. So if you've got a NetApp, an Isilon, or some other type of traditional NAS storage, it can take that data from the application and put that up in the cloud. It also, because this is a blob storage session, it pulls data from blob. So if you have an application that you have moved to the cloud that is a file-based application, you can in fact store that on an object store. So Azure will write that data into blob, but present it as a file format to the compute farm. And so that our caching layer is spun up adjacent to the compute to get the low latency you need for those types of applications. So that's, in a nutshell, the VFXT for Azure is. And this week we announced, we are in public preview, we have been for the last month and a half, but we announced here at Ignite that the product will go GA at the end of October. So we're pretty excited about that. But right now, if you were to go out to the Azure Marketplace, we're a first-party marketplace product, so we're a Microsoft product actually on the marketplace. You can go out there and you can find Azure. Okay, so I talked really briefly about cloud bursting. I've only got a few minutes, so I'm going to run through these very quickly. So cloud bursting, this is the idea of your storage is on-prem. You move that compute up to the cloud. You do not need to copy all of the data. You're only going to take your working set. So you're going to create a cache that is sized appropriately for your working set. You're going to copy that data into the cloud, process it, and then write it back down onto your on-prem storage. So you don't have to take, so let's say you have like a petabyte of total data, you're not taking that entire data set up to the cloud. Maybe you only need to analyze a couple terabytes at a time. So that's what you'd be doing. People love this. It's so easy. You can get going in a few hours. There's no capital outlay. You spin up your virtual cluster. And in fact, in many cases with cloud bursting, people are using low priority VMs. So they're doing this processing because, again, there's no humans involved, right? Calling and saying, I don't want to work at 2 in the morning. It's a compute farm. So when there's excess compute available in whatever region you're looking for, you can oftentimes get a much better price in using a low priority VM. And that's what many of the HPC customers do. But there's also lift and shift. We have folks, and particularly in the life sciences vertical, with entire genomics pipelines, have taken and moved those pipelines into the cloud. And oftentimes they get started with cloud bursting, get comfortable, get familiar, and then they take and they move that storage up into the cloud. But instead, now the storage repository, instead of residing on-prem in a NetApp or an Isilon, is now in blob storage. And so in that way, everything is all in the cloud and there's no writing back to on-prem. I just have one picture here just to show you kind of a representation of what both those cloud bursting and all-in-cloud use cases look like, kind of in a pictorial with the representation of both the cloud and the on-prem environment. You can see that one of the most important characteristics we have in a cloud bursting environment is express route. So for HPC applications, we absolutely positively need a high throughput, high bandwidth pipe going from your on-prem environment up into the cloud to move that data, to do the right pulling of the data and reading into the cache, and then the writing back down to your on-prem storage. The link between Blob and the Azure Compute Farm would be an in-network, in-cloud type of connectivity. All right, I'm just going to maybe go through 2 more slides and wrap up because we are at the end of time. But a couple things I did want to talk about is that, so Azure VFXT, because it was built for HPC applications, it's not your it's just not a standard cache, right? It is a clusterable, highly available cache, nodes in a cluster, and it's a minimum of 3 nodes in a cluster, and that's for high availability purposes. But they'll share configuration information, so if one goes down, or you have to replace one, or you join one, you don't have to replicate that information. The consistency information is there, and the metadata, you don't end up with a bottleneck. The metadata is spread across the cluster. We support 2 instances now, 2 SKUs within Azure. Those are largely based on availability within regions, so we're always looking at that, and we're looking at cache size. Those will change over time depending on what the compute team in Azure is offering up. And then our average customer runs about 3 to 6 nodes. And for an example, you can see that we have folks, running, 6,500 cores with just 6 virtual nodes in Azure. And then I thought I'd just mention really quickly, high availability, very, very important. Each node in the cluster has a buddy peer. Because it's a read-write cache, there's always a partner. So when you acknowledge a write, it's then act to another peering buddy within the cluster. That way, if one goes down, you never lose any writes that are still in the system. All right, so I'm going to skip past all of this stuff. You can go online and look. There's some really great information about how the system works. But I'm going to kind of go to the very end since I've just got 1 minute here. We've got great use cases. I've talked about some of them. I've talked about life sciences. I've talked about media. Here's one which is EDA, a tools repository. So a lot of manufacturing, they use the same tool set over and over and over in a pipeline. And if all of the VMs need that to be available, caching is really a great way to deal with that. We have a very large customer in Azure right now that is doing this. So that's pretty exciting. Lastly, I'm going to leave you with this, the use cases for Azure in your organization. So if you have HPC applications within your organization, here are the things you need to look for. Does it support NAS protocol? So not SAN, not anything else. So it's got to support NFS v3 or SMB, right? File serving. So we're not looking for anything that has a lot of users attached to it, like home DIRs, not a great fit. Looking for big compute farms, 1,000 to 100,000 CPUs. Azure can certainly cache in smaller instances. It's just that the economics usually don't work out well for caching when you go below 1,000 cores. Even though it's a read-write cache, writes will slow down the operation of the cache. So predominantly read-heavy, something on the order of at least 90% read an application, 90% reads, 10% writes. And then we like standard NAS to work with if we're working with on-prem, like from a NetApp or a Dell EMC Isilon. There's a lot of homegrown NAS out there that can be a little more difficult to deal with from a semantic standpoint. So I think that's it. I'm a minute over, and thank you so much for your time today, and I'm going to pass it back to Vamshi.
Thank you, Rebecca. All right. So just a quick wrap up here. Saw these 4 different patterns. Hopefully these are interesting, give you some ideas about what we can do or how you can apply these. Any questions at all, please always email us, Azure Storage Feedback. And last but not least, if you're interested in coming out for a beer after this, they just started in rooms W208A and 208B up till 6 p.m. We'll be there. Come on up, get a ticket from me or from Klaus. We'd love to see you there. I'm also happy to stick around and answer questions here if you have any. Thank you.